I'm going to speak about a method to try to solve a lower bound to an optimal control problem, and the approach is to use occupation measures. So I'm going also to recall what I mean with occupation measure. So I have two outlines for this talk. The first one is the main outline. So first, we are going to consider an optimal control problem, and the first step is to rewrite this this optimal control problem with occupation measures that I'm going to define just after. And when you use this kind of formulation, you obtain what I'm going to call an infinite dimensional linear programming. So what is incredible with this approach is that even if the non-linear, the optimal control problem is non-linear, you always obtain a linear problem. But the price is that now you have an infinite number of variables. So then I'm going to show you how it is possible to use interval analysis to relax in a guaranteed way this infinite dimensional linear programming problem into a finite dimensional linear problem. This is what I'm called the LP problem. And finally, of course, as you know, there exist many solvers to solve this kind of linear problem. And during the approach, we take care to be sure that we obtain guaranteed lower bounds to the problem we are looking for at the beginning. So this is now the true outline. So in the beginning of the talk, I'm going to give you some recalls about measure theory. Be careful, this is not, I'm not going to speak about measurements and so on. I'm going to speak about Lebesgue measure, Dirac measure, kind of distributions. So I'm going to show you how it is possible to, from a trajectory, to create two measures. This is what I'm going to call occupation measure. Then it is possible to integrate a function with respect to this measure. And also, when you have an ordinary differential equation, it is possible to rewrite this ordinary differential equation into a linear equation over the occupation measures that we are going to consider. So the first part is really about measure theory. It's maybe the most important part to understand. This is a bit theoretical, but this is not my my main resource, because this is something which is already known by the community of control theory. And then at the end of the talk, I'm going to show you how it is possible to relax rigorously this this linear problem into a finite dimensional one. And I'm going to conclude by an example. So, a measure. So a measure, here it's a bit technical, but you can think a measure as a function that from a set compute a real numbers. So the first assumption is the following. You want that every set has a non-negative measure. I can also say a mass of this set. The mass of the empty set is equals to 0, and this one it seems to be technical, but it's quite easy. If you have two disjoint sets, the mass of the union of those two sets, it's only the mass of the first one plus the mass of the second one. So here, a collection of pairwise disjoint sets and so on. So in the theory, you need not to consider all the subset of X, but only a certain kind of subset. So, examples. So there is this famous measure created by Henri Lebesgue. It's going to assign a number to every intervals. So, for example, the mass of, or the measure of the interval AB is equals to B minus A. So from this, if you have the mass of some sets, for example in this case, now if you have a more complicated subset of Rn, all you have to do is to decompose this set onto intervals, then to add the measure on each interval. So that's why I only define the Lebesgue measure for intervals. Then there exists another famous example, the Dirac measure. It's a measure that assigns sometimes 0, sometimes 1, if the set contains the number A. Sorry. So this is a mass which is located at only one point. So it's really a measure because it assigns to a set a number, non-negative number. And the last example, before I introduce the special measure according to an ordinary differential equation, if you have a function, maybe a non-negative function, you can, for each set, compute the mass of this set with respect to this measure, which is only the integral of f on this set. So now occupation measures. So I need to give you two occupation measures to continue. So the first occupation measures I'm going to consider is the following. So you have a trajectory or a parametric equation for a curve. We define, this is nu, so there is a mistake here, nu of E. This is simply a Dirac that you place at the end of the trajectory. So now if I have my set X, I can say that the measure of the set E1 is equals to 1 because E1 contains the end of the trajectory. And this one is 0 because it does not contain the end of my trajectory. So this is nu, the first occupation measure. Now there is a second occupation measure that I need to define. So this one, it's a bit different. It's going to count how long time my trajectory goes inside the set. So for example, if you take this set E1, I'm going to assign a non-negative number to this set E1. It's going to be how long time does my trajectory stays inside the set E1. So for example, here you have your trajectory, the time here you can see the curve. At time t1, my trajectory goes inside E1, and at time t2, it goes outside. So I'm going to assign the number t2 minus t1 to this set E1. So, and for this example, it's going to be 0 because my trajectory does not cross the set E2. So what I have defined two measures, a measure depending on the end of the trajectory and a measure depending on the whole trajectory. And I want to be sure that everybody understands that if you have this measure, you can create the path. Because all you have to do is to give, for example, E2. As you know that the measure of E2 is equal to 0, you know that your trajectory is not going to go into this set. So now, as soon as I have a measure, I would like to integrate a function with respect to this measure. So let me consider first a parametric equation and also a map which is defined on the state space. So the map H is defined all over the space X, and I would like to compute this integral. So this is the integral of H with respect to this occupation measure, mu, for example. So what I want to compute, it's some kind of area which is under the graph of H, and this is not very difficult to show that this is equals to this area here where y depends on t. You just compose your two maps. So this is the first proposition. So this proposition says like I can integrate function over the state space with respect to a measure, but the measure assign the support of the measure is only a one-dimensional set. So for me, when I discovered this kind of theory, it was a bit weird because during all my life, it was only the Dirac. So you put all the mass at what point, and also density with respect to Lebesgue measure. So you have a mass which is everywhere on X, but here it's a kind of one-dimensional Dirac, could be said. So now I'm going to show you that this is the more technical. I'm going to show you that if you have an ordinary differential equation and you also have a finite time, capital T, your your two occupation measures satisfy a linear equation. So here you have to see something like this. A equals B, where B is going to be a Dirac at the initial position, and A, it's what I've called L, because this is Uville who has created this approach, and X is given by the vector of two measures, which is how long time do I stay in a set, and a measure with respect to the finite time. So this equation, it's a linear equation with an infinite number of lines and an infinite number of columns, rows. So how can I define L prime? I have to use duality. So let me explain in the proof. The proof is going to be on this slide, so it's not so long. So first, I have to use the fundamental theorem of calculus when you want to have a map, and you said that the difference between the final time minus the initial time, this is just the integration of your map with respect to the differential with respect to t. Then, here you can use chain rule, because you want to differentiate with respect to t, so you can here compute a gradient, because phi is a map from Rn, from x to r, so this is just a gradient. And here you just write the derivation of x with respect to t, so you obtain the velocity. Now, as you know that the x satisfies the ordinary differential equation, you can replace x by f of x. And this is here maybe the most difficult, because, as I said, you can replace a time integral by a space integral, but now with respect with your new measure. So here you can see t. There is no more t in this equation because I integrate with respect to space. This is the main difference between those two. Here you can see that the evaluation of this function at time, at x0, this is just the integral with respect to the a Dirac placed at x0, and it's the same for this one, because nu, this is just a Dirac placed at the finite position of the trajectory. Also, this is a notation I'm going to use for the rest of the talk. If I have a map that I want to integrate with respect over the whole space, I may write this. That's a notation. Okay. So I'm going to rearrange everything here. So I put this on this side, this one on the other side. So now you can see that I have those two measures. It's the Cartesian product of two measures, so it's a measures. Here is the map that assign for each function this function. It depends only of x. And at the end, I have to use a duality. Let me explain what it is. This is not very difficult. It's the same thing as when you are in finite dimensional case. If you want to compute the dot product of y with ax, you know that this is always equal, the same as this one. So you can place the A here or A transpose here. So I do the same here to put the linear map L onto the measures. So as you can see, the equation 4 becomes this one. As soon as it is true for all function phi, I can write this linear equation. That's all. So it creates an equation of the form ax equals b for any differential equation. Now the unknown is the occupation measure. So let's go into the optimal control theory. So a controlled dynamical system, it has already defined before. This is the definition I use. And for example, in this case, what I have the initial condition, which is 2. I also have the vector field, which is equals to the control. And I also have the constraints on the controls, which says that the velocity may be bounded by -2 and 2. So what does it mean? It means that the slope of the curve cannot be bigger or less than a minus and +2. So I can do it everywhere, and of course I can draw trajectories. For example, this trajectory satisfies the constraints, but this one does not, because the tangent to the curve is not contained in the interval here. So now, when I have a controlled dynamical system, sometimes you want to find a best solution. So a way to write the best solution is the following. This is almost classical. So what is it here? Here in red you have your control system. So classical initial condition. Also you have the dynamics here, and you also can have constraints on the state space, constraints on the time. You want that t belongs to 0 and capital T, and you can also have constraints on the final time you want to go to this target, for example. And what I want to minimize is the integral of something that depends on the state, the control, and the t, the time. In a classical control theory, H, it's called the running cost, because this is something which is it's like your cell phone. You have paid you pay €1 for 1 minute, so it's a running cost. And here you had also something that depends. That's the final cost. So you have two costs. It's almost general. And with the demonstration I've shown, it is possible to rewrite this nonlinear optimal control problem into a linear program. Let me explain. So this integral with respect to t can be replaced by an integral with respect to x, but with respect to the measure mu, which satisfies this equation. And also here, as h of x capital T, this is just the evaluation of big H or capital H. So all you have to do is to do this integration. And also here you can see in red, this is the same as this one. This is the proof I've done just before in the first part. And you can see also the constraints on the state space and on the control, which are embedded into the support of my measures. And one has, this is a theorem from Winter. He shows that under some assumption that I have not had here, but classical assumptions, that there is equality between those two optimal values. So maybe a remark, an important remark, is that this problem is an infinite dimensional linear programming problem. And all the details can be found in this paper. So now I'm going to take this infinite dimensional linear problem to relax it, to be able to have a finite dimensional linear problem that can be handled by the computer. So here I'm going to use interval analysis, as most of you knows how it works. I'm not going to spend a lot of time with this, but if you have a set, an interval x, you can, of course, mathematically define the range of this function on these intervals. And what does interval arithmetic, it can create, it's not the only way, but it can create an inclusion function that is something which is bigger always than the range of this map. So as soon as I have this, it is possible from a partition of x, so here x is just this segment. I'm going to divide this segment into 5 segments in this example, and I want to enclose the integral of this function with respect to this measure. It is possible just to add those two sums, and you obtain guaranteed bounds for the integral. So now, if I want to solve this problem, what can I do? It's first, I create a partition. So as soon as I have a partition, I'm not going to compute all the measure explicitly. I'm just going to measure some kind of sets. So I'm just going to measure these sets. Also, so I create from this here. From the first one, I relax, using interval analysis, the constraints. Not the constraint, the cost. I have a smallest cost. But I have also, again, an infinite number of constraints. So if I have an infinite number of constraints, I just consider just a finite family of functions with indeterminates t and x, and it gives me, according to the theorem I've shown just before, to enclose an integral, this equation which is in red. So I have a cost which is smaller, and I relax the constraints, so of course I obtain a minimum. This minimum is smaller than the optimal that I want to compute at the beginning. So let me consider this example. It's a classical one which is present in many books about optimal control theory. It becomes first this infinite dimensional linear programming problem. You can see this is just I rewrite differently. Then it can be relaxed according to what I have shown before. You can choose your finite family of function phi to be this kind of functions. According to the Taylor theorem, it tells you that you can approach any function phi, so it could be a good way to use these functions. But you can also use sine, cosine, so whatever function you want. Each time that you add a function, it constrains a bit more your system. So it's better for the solutions. So let me look at this one. So here you have the 3D representation. This is time, this is the state, and this is the control, as I remember. Yes. I just divide each. This is just to explain that there exist better strategies. But I just divide this set in every set into 10 subsets. So it's going to be create a linear program with 1,000 variables. And I just choose the 10 constraints arbitrarily. Not completely, but almost. And of course, for a linear solver, it's very easy to handle 1,000 variables. So here is the output. So how do you read this output? Here it is the subpaving, and this is the output of the algorithm. So I did not represent on this figure every box such that the measure of this box is equals to 0. So this is where does the trajectory should go. Now I can have a better precision. Let's create this kind of huge linear programming problem, but it could be solved in maybe 1 second. Works very, very well. And well, so for example, I was able to gives me maybe less than 1 minute to solve such kind of problem. And if you do this way, here you can see the precision. And for this example, it's very nice because you can compute explicitly the optimal value. So you can add, you can see here, as long as we divide our set, that the optimal of the lower bound converge to the optimal value. So let me conclude. So at the end, the software I've used to develop this algorithm is Philippe GLPK to the part about linear programming, GMP also to find a perfect solution without rounding errors and so on. The source code is available on my webpage, and all the details can be found, not of what I have implemented because it's not already published, but the main ideas to use occupation measures and how to relax in a paper of Jean-Bernard Lasserre and Didier Henrion. And in their approach, they do not use interval analysis, they use sum of square instead of, but it's quite the same idea for the first two parts of my presentation. About future work now, as we have a linear programming problem, we can also generate its dual. This is classical in linear programming. And what is nice is that when you do this, you obtain a solution or sub-solution to the Hamilton-Jacobi-Bellman equations. So it's nice to have this. I would like also to combine these methods with the mean plus superposition principle to provide solution to the Hamilton-Jacobi-Bellman equations. And a future work I really want to do right now, it's what I've presented here. It creates a family of constraints about this ordinary differential equation. I know it's not easy to see here an ordinary differential equation, but there is an ordinary differential equation. And I think that we could, from this approach, create a new way to solve ordinary differential equation just by solving a CSP, a linear CSP. Merci pour votre attention.
Thank you for an interesting talk. We've slightly overspilled into the question and answer session, so perhaps if we could keep the questions brief. Who would like to fire off?
Maybe a small question. So you use interval analysis for the discretization?
Yes, only.
And how it works for the LMI approach? It is the same, they use the LMI approach, the sum of square approach, only also for the discretization?
Yes, that's it, exactly. The difference between our approach and the one by Didier Henrion and Jean-Bernard Lasserre is that at this point, here, as they use moments, this integral, the cost is the same. So they don't have here a lower cost, but they create, they use sum of squares.
Okay.
But with their approach, this number here is the same as this one, but they relax the problem here. The infinite number of linear equations is transposed into a finite number of linear inequalities, NMI.
Anyone else?
But this is the main ideas, the same ideas.
Maybe an equation. Why don't you compute the upper bound of the?
Oh, here it is. Because if I compute here maximum, it's going to be something bigger than this one. But as soon as I relax the linear equation here, I can create a I don't know the word in English. I can create bad solution that does not respect this constraint. So that's why it does not work for the upper bound. But the dual can do it. So that's something I want to do also.
I think in the interest of time we need to move on, but let's thank our speaker and ask